Good morning. Welcome to Basics of Finite Element Analysis. This is the last day of the second week of this course, and what we are going to discuss today is again we will do concept review, and today we will focus on this term called functional, and then if we have time we will also introduce another term called variation, because both these terms, functionals and variations, they are heavily used in finite element analysis. So, we will start with functionals, and if we have time then we will start also the variational discussion on variation and variationals. So, that is what we are going to talk about. Now, consider, so we will start with an example. So, suppose I have this plot of a function f x and some function. So, my y equals f of x, or I can, because I am going to use this letter u, so I will say that u is a function of x. And suppose I am interested in finding the length of this curve. So, how will I do that? So, I am interested, so suppose u is f of x and I want to find out the length of this curve. So, the goal is find length of the curve for the range x a to x b. So, what do I do? Basically, let us say for a very small element, for a small portion of this curve, let us say this length is ds. Then I can write down that ds equals, so if I zoom in on this, then it will be something like this. So, this is ds, this is change in y, so it is du, and this is change in x, dx. So, ds is equal to du whole square plus dx whole square, and I take the square root of that. Okay. And if I, because this x is, u is equal to f x here. So, if I take x out, then I get 1 plus du over dx whole square, and dx is out. So, that is the length of a very small element on the curve. So, if I add up all these small elements on the curve, then I get the total length. So, S, which is the total length of the curve, this equals, so this is total length of the curve between limits x a to x b. So, this is equal to, I can integrate x a to x b ds, and because I have calculated dx as this, so it is x a to x b 1 plus du over dx square times dx. Okay. So, that is the total length of the curve. Now, to compute the value of S, I have to know U. To compute the value of S, I have to know U. So, U could be anything, U could be a straight line. In that case, U could be represented by Ax plus B. If it is a parabolic function, then U would be Ax square plus Bx plus C. If it is a cosine function, then U would be A sin pi x or some A sin pi x or some function like that, and I can have infinite types of functions. The point so the point what I am trying to make here is that the value of S in this case depends on the nature of U, the nature of U. So, I can write this S, it does not depend on anything else, right, because du over dx, it also depends on the nature of U. So, I can write S as S is a function of S of U. If I change U, then S is going to change. These types of integrals are known as functionals. So, I will make a general statement. So, to make something general, let us say there is an integral x a to x b, and it is an integral of some function which depends on x, which depends on u, which depends on u prime, which depends on u double prime, and if I integrate it, then this thing, the integral of this entire expression is called functional. Okay. So, the example which we had discussed, so in the earlier example, the one which we had discussed, f for the earlier example, f was defined as 1 plus u prime whole square like this. So, this is just an example, but f, this is a very generic statement that if there is a function which depends on x, u and derivatives of u, and if I integrate that function with respect to x over a limit, then whatever I get out of that is known as a functional. Okay. So, in some sense, in a very loose sense, I is nothing but a function of functions. Okay. What are the different functions? One function could be u, another function could be u prime, another function could be, and so on and so forth. But this is a loose definition. Okay. But the point to remember here is that when I change u, the value of I changes. So, I depends purely on u. So, that is why I say that I depends on u, it depends on u, and this is a functional. Okay. Another example of functional. Suppose I have another, so suppose I am plotting here ux, so some function, and on the x axis, this is the x axis, and suppose I am interested in finding this area So, this is the area. So, suppose I am interested in finding the area under the curve. Okay. I am interested in finding the area in the curve. So, goal is find area under the curve between x a and x b. Suppose that is what I am interested in finding out. So, what is the area? It will be basically U area, it will be ux dx integral x a to x b. Okay. So, that is the area, and so let us call this area as A, and depending on our choice of u, the value of this area is going to vary. So, I can say that this area is it depends on u. If it is again based on the nature of this function u of x, area is going to vary. So, A depends on u in this case. So, it is a relatively simpler functional where the dependence is only on u and not its derivatives. In this case, it was a little more complicated because there was this u prime, and then I had to square it and take square underscore the square root of all that stuff. So, it was a little more complicated, but this is the general definition of functional. Mathematically, I is defined. So, mathematically I say I is a functional if it does one important thing. So, it is a functional if it is an operator. It is an operator. So, what is the operator in this case? This whole thing, this is the entire operation we are going to conduct, right. So, that is why it is an operator, we are conducting an operation. So, it is an operator which maps u into a scalar that is IU. Okay. So, IU will be a number, so it will be a scalar. So, it maps u, which could be in vector space, and it maps it into a scalar quantity. Now, in context of this particular course, we will be dealing with a lot of functionals, but they will belong to an important category called linear functionals. Linear functionals, and we will write them as LU. This is the terminology we will use. So, I can say this is the, so a linear functional could depend on some function u, and it can also, so one thing before I explain this linear functional is that in this case the dependence is only on one function u and its derivatives, but there is no rule that functional cannot depend on only one function. It can depend on several functions. It could be a function u, another function v, and so on and so forth. Okay. So, the property of a linear functional is that it is a linear functional, then, and I will explain this. So, this is the property which linear functionals obey. Basically, this is the law of superposition. What does it mean? That suppose you have a functional, I and it depends on u. Okay. Suppose there is a functional I and it depends on u, then the first rule which this functional has to obey is that if I multiply u by a factor alpha, then its value will be same as alpha times IU. This is the first thing. So, this statement is a combination of two different statements. This is the first thing, okay, that if I have a functional which depends on u, then if I multiply instead of u I use alpha u as the input, then the value of this functional will be alpha times IU. This is one thing. The second thing is, if I have a functional u and a functional of u and there is, and then I also compute it for another function v, right. So, this is I1, this is I2. So, I compute two different values for I1 and I2, and then what I do is I compute I for u plus v, then this will be equal to I of u plus I of v. So, this is the second condition, and both these conditions, so if it meets these two conditions, then it is a linear functional, and what I have done is I have combined both these conditions in this statement. Okay. So, this is that is the definition of a linear functional. To illustrate something, this thing. So, suppose there is a function u of x, okay, and I am interested in finding the area below it. So, I will call it A1. And okay, and let us say this curve u of x is represented by some constant k times u, excuse me. So, this is some constant times u of x, okay, and I have another function, and let us say here I have v of x, and here also I am interested in finding this area under the curve, and let us say I call this area A2, okay, and let us say this function is represented by, I have okay, so instead of k I will use alpha, because I have used alpha here. So, here let us say this is beta of another, beta times another function v. So, I did not say this alpha and beta are constants. Okay. So, if I add these two areas, then I get A1 plus A2. Now, I create another functional which corresponds to the sum of these two individual functions. Okay. So, this is another functional which corresponds to the sum of these two functions. So, here what I do is I am going to plot u plus v. Okay. So, I get some third curve, and this curve is represented by alpha times u plus beta times v. Okay. So, how do I generate this curve? I basically get this point from here, I take individual points and I add up the values for all the points. So, I get my total sum of those two curves. Then, and now I am interested in finding this area A3. Okay. So, I integrate this whole curve and I get this A3 curve, and what I will find is that A1 plus A2 will be A3. So, what in that case what do I say? That the functional I of u which represents the area under the curve is a linear functional. That is L of u. It is a linear functional. Understood? So, that is what it means, because I can add these. If A1 plus A2 did not come out to be same as A3, then it would not have been a linear functional. It would not have been a linear functional. This functional, which we have discussed earlier, is not a linear functional. It is not a linear functional. Why? If you take one curve, what does this this functional? This represents the length of a curve. If you take one curve and add to it another curve, the individual lengths of the two individual curves will not be same as the length of the sum total of those two curves. Okay? It will not be same as the sum total of those two curves. So, this is a different type of function, but it is definitely not linear. So, now we have discussed what is a linear functional, and next what we will do is we will talk about a functional which is called bilinear. Bilinear functional. So, in such a situation, we are here, we deal with functionals which depend on two functions u and v, and they could be mutually independent. They could be two functions which could be u and v. Okay. This bilinear functional is represented as B, standing for bilinear, and the two functions which we are talking about are v and u. Okay. So, what is the attribute of bilinear functional? First thing is, it is linear in u, and it is linear in v. So, if it is linear in u, if it is linear in u, so actually I am going to just change this, it is u and v, okay, just to be consistent. So, if it is linear in u, then B of alpha u1 plus beta u2 v equals alpha B of u1 comma v plus beta times u2 comma v. That establishes the linearity in u. So, a bilinear functional has to be both linear in u and linear in v. So, if I am having u itself is a sum of two functions u1 and u2, then if I compute the value of that functional for u1 alone and u2 alone, and I add those two up, it should be the same as the value of the functional which is calculated using u1 plus u2. That is what it means. Okay. So, this is the condition for linearity in u, and the condition for linearity in v is that, so it is a very similar formula. So, here instead of u1 and u2 we will have v1 and v2, and let us say alpha times v1 plus beta times v2 equals alpha times b of u v1 plus beta times b of u v2. Okay. Once again, alpha, beta are constants. So, a bilinear functional, first thing is it depends on two functions, two independent functions, okay, two independent functions, and both these functions could be functions of x, and it will be linear if it is linear in u and linear in v. It has to satisfy both these constants, both these conditions. Okay. And then there is a special category of a bilinear functional, and it is symmetric. Symmetric bilinear functional. So, what is it? It is symmetric if b of u and v is same as b of v and u. So, we will give examples for that. So, then it is the condition for symmetry is that if you have a bilinear functional depending on two functions, mutually independent functions u and v, and instead of u you put v, instead of v you put u, the form of the functional should be same, the value of the functional should be same. So, then it would be a bilinear functional. Examples: so, let us consider I of u is equal to integral 0 to L of x times f of x times dx plus dv over dx x is equal at x equals L times some constant m naught. Okay. So, here m naught is constant, v is a function of Vx, and this is a functional. So, I should have written it here as V. I should written it as V. F is known function. F is known function. So, I cannot vary F. I cannot vary F. V is something, let us say we are interested in finding out. We can change. So, this is, so that is why I am saying that I depends on V alone, it does not depend on F. F is known, so I don't know, but it is the V. If I change V, I cannot change F, but I can change V, I can change V. So, if I change V, then I changes. So, that is why I is dependent on V alone, okay. And then m naught is also a constant. Okay. So, this is there. Now, if I replace V by alpha times V, right, what will I get? I will get this condition, I of alpha V is equal to alpha times I of V. Also, if I replace V by U plus V, then I get I of U plus V is equal to I of U plus I of V. I mean, I can do that, right. So, both these conditions are satisfied, which were the conditions for linear functional. I can satisfy both these conditions. So, I can say that it is a linear functional. I could have directly, instead of doing those two conditions, tried this thing, the first condition, which is a combination, and it would have satisfied that also. Okay. So, and I have to use that condition also in this term, okay, because I am not defining I as just only this thing, I am defining I as the entire sum of this thing. Okay. So, I should make these operations in this term and also in this term, and then see whether I is meeting those conditions or not. Okay. So, that is there. Let us say another example of symmetric P of UV. So, this is an example of symmetric bilinear functional. So, let us say that I UV equals 0 to L A of x du of dx times dv of dx times dx. Okay. And Ax is known. Okay. So, again, if Ax is known, these are the things we can, I can change u and v, right. I cannot change A. For instance, A could be the cross sectional area of a rod along the length, that is not going to change, but u and v we do not know. We can try different solutions for u and v and see whether it will meet our needs or not. So, that is why, so I depends only on u and v. I mean, of course, it depends on A, but that dependence does not change because A is not changing. Okay. So, I is of depends on u and v, and if I replace u and v with each other, this entire expression does not change. So, that is why it is, first thing is it is bilinear, because if I use this condition, what is the condition for bilinearity? That it should be linear in u and linear in v. So, I verify whether this condition is satisfied, the first condition is satisfied, and I will see it satisfies the first condition, and I will also see that it satisfies the second condition. So, that will establish that it is bilinear, and then I will go further and I will replace u with v and v with u, and then I see that the form of I does not change. So, in that case, so because of these two reasons, I of u and v is, first thing is it is bilinear and it is also symmetric. It is also symmetric in u and v. So, this closes the discussion on functionals. We will not cover the idea of variations and variationals in this lecture because of lack of time, but starting next week we will start with discussion on variations, and then we will start looking in detail at weak formulations. So, thank you very much and have a great weekend.